Hello, welcome to this video that's part of CNG 41 Statics in Santa Clara University. My name is Dr. Hisham and I will start the video with a very quick demo exercise where I have here, that's my beloved foam beam that I use a lot to explain concepts in statics and strength of materials. And what we'll do is imagine it's a real beam and it's loaded in the middle, here. So this is the kind of a free body diagram, simply supported at the ends. And the beam has this rectangular cross section, 19 millimeters the height, the smaller dimension, and then the width of the cross section is 39 millimeters. And we'll load it in the middle using that my lunch bag. Very delicious lunch I had today. So what I will do is I will load it, the cross section is this way, so the 39 is kind of the horizontal dimension in the middle, and I will use my hands or fingers, kind of the supports at the ends, and as you can expect when loading a beam, it deforms or deflects. Now, this is too much deformation compared to a real life example or cases. Otherwise, people will start screaming and running around. It's very scary, beam to look or walk on. So, question to you is now, if this is a scary, too much deformation for a beam, how we can reduce the deformation or deflection of this beam? And I will make it more challenging question to you by putting more constraints on it. So first of all, load stays the same. The beam material stays the same, so it's foam still. You can't bring the same beam dimensions wise and just change it to timber or steel or concrete. Dimensions stay the same, lengthwise and also cross section wise. So everything's still the same. It's just now how you can do a little trick to reduce your deformation from this bed. So I'll give you maybe 5 seconds or so to think about it. I think I can hear the answer. People starting murmuring and saying the correct answer, which is change the orientation of the cross section. So it's originally loaded this way. So the vertical dimension is the 19 millimeters. Some of you are saying now, let's do it this way. So the vertical dimension will not be 19 anymore, it will be the 39. 19 will be the horizontal dimension of the cross section. And then if I load it, now you can see it's still deforming, but it's much more appealing and comfortable looking at than this. So this is the deformation when we load the beam with this cross-section orientation. Now this is the deformation when we load it with this cross-section orientation. So if we think about it, now we have two load cases of this beam. So I'm thinking or drawing down these two load cases. Same beam, same everything. Dealing here with case 1 and case 2. And the deformation here looks like in the first case, which is this one, which I should draw actually the cross section for it. So the cross section was looking this way. The other case, the cross section was flipped orientation wise 19 degrees. So the deformation we found kind of it is deforming this way or this much. In this case it deformed but much less. And I will call the deformation in the mid span here delta. So this is case 1, delta 1. This is case 2, delta 2. And we found here delta 1 is more than delta 2. So this is an example of good engineering decision. You don't have to consume a lot of resources, just a matter of using wisely your resources. So instead of, again, loading it this way. Question is, from statics point of view, what did change here? What really this orientation of the cross section changed to make the deflection smaller this way? So we'll learn about this more and the moment of inertia, or the second moment of area, after the commercial break. Hello, welcome back. So now we did in the first part this quick demo, and we used the foam beam to figure out now under different orientation of the cross section what's the deformation. We found that when the cross section is on its flat side, it gave us more deformation or deflection mid-span than when it's on the shorter side to be like horizontal dimension. And we found that the delta 1 is more than delta 2, and we asked the question, why is that? So it all goes back to the moment of inertia, or the second moment of area. But before we're jumping into moment of inertia, or I, let's see how I is related to the deformation in some way. So from strength of materials, which is of course if you are a civil engineer or a mechanical engineer major, you will move to CNG 43 or 44 to study strength of materials. And in strength of materials, you will drive this relationship for that specific load. So the deformation or deflection mid-span is equal to PL cubed over 48 EI. That's one specific formula for this specific loading case. If you have distributed load or other distributed load or other cases of loading, like you'll see, for example, you can see table. You will have tables and tables of the typical deformation and deflections of typical loading cases. But for us, this is the load case, and this is the corresponding mid-span deflection. Now, this deflection is dependent on a couple of things. First, the load P. The more load you'll have, the more deformation you'll have. The length of the beam. So if the length of the beam is shorter, you expect to have less deformation. E is the Young's modulus of elasticity. So that's a property of a material. So steel has E different than wood, different than foam. So it's a material property, and then I is the moment of inertia. And remember the constraints I put on you to figure out how to figure out this orientation is basically I try to fix all the values you have here except for I. So I told you don't change the dimensions, meaning L, don't change P, don't change the material E, so you end up with in some way I. So if you try to compare now this delta and delta, everything in the formula, P is the same, L is the same, divided by 48, E is the same. The only difference that we made, which trust me here, until you understand why the I here is different, so I'll call this I1, is more than this PL cube over 48 E I2. So everything here cancels except for I1 and I2 because they're not equal. So you will find that, you know, flipping the formula and all that, you will find that you had less deformation for the second case because I2 is actually more than now I1. I will actually flip it so you can keep the left case or the left side as I1 and I2. Now the moment of inertia is more than the moment in the second case, more than the left case, and this is why you had less deformation than the first case. So what's really the moment of inertia here? So moment of inertia is the geometric property to indicate of a cross-section ability to resist bending. So if we have transverse loading, at the end internally the beam feels bending moment, and that bending moment causes that in some way causes deformation here. So the resistance to the deformation is a property reflection of how much I the cross section has. So I is Another name for it is the second moment of area, and second moment because you are basically to the power 2. You're similar to the first moment of the area, which we used to find the centroid of a shape. Now we're kind of dealing with the second degree of it. So Ix is equal to the integration of the small dA times the distance from the x-axis. So this Ix is resisting the moment around the x-axis by figuring out that y, kind of its function of the y dimension of the cross-section. Iy, similarly, is integration of the dA for all the area A, and then for every dA, you're multiplying by x squared. So the moment of inertia is an indication of how tough the section to resist bending and the deformation of it, or the deflection that comes with this internal bending. So the good thing is we don't have to do integration for all the shapes. So in the third part of this video, we'll see the typical I, or moment of inertia, for typical cross-section shapes, and we'll apply it here to see really how much is that difference in I to cause that much in deformation in the beam. So bear with me, we'll wait for you in the third part of this video. Welcome back. So continuing with this concept of moment of inertia, so we learn how to calculate it theoretically as, dA times y squared if you're dealing with Ix and doing the integration over this whole area, and dA is a small area of it, so you do the integration to cover this whole cross section. But just pay attention here that y is measured from the x-axis going through the center of gravity. So you have to first do, similar to the exercise we covered before early in the class, figuring out the centroid, or the center of gravity, and that's the x-axis, nothing else, to calculate the Ix of the cross-section. Iy, similarly, is the x measured from the y-axis. dA, and then x to the power 2, you do the integration for the whole area. Now, we don't have to do that for all sections, because most of the real-life sections are simple cross-sections like rectangles, or made of rectangles and other shapes, circles, half circles. So we're lucky that textbooks provide already tables of such geometric properties, including the moment of inertia. So for our case, we're doing with a rectangle. I is equal to bh cubed over 12. So, and I'm saying here Ix, but the key here is really knowing what's b and what's h. So for our case here, we have two orientations of the cross section. So we have this one, and we have this one. So x-axis is the one that we have the moment around. So if I have the cross section this way, and I'm loading here, and it's bending this way, it's around the x-axis here. So that's mx. If I change the orientation, x is the horizontal axis still, and the moment is still around this horizontal axis. So for both orientations of the cross-section, x is the same. What I'm changing with the orientation is b and h. So for the first case, b, always b, is the dimension parallel to the x-axis, if you're dealing with Ix. While h is the perpendicular to the x-axis. So parallel to the x-axis in the first case, this is b. Parallel to the x-axis in the second case is the smaller dimension. While h is the dimension perpendicular to the x-axis, so the whole height, h, and then the second case, this is h. So I'm dealing now, this is case 1 and case 2. So what we can do now is calculate for each case what's the moment of inertia. And we can see now how the difference in the moment of inertia gives us that difference in the deflection. So for case 1, Ix, my dimensions are 19 and 39. So B in that case is the biggest one, 39 millimeters, I'm sorry, 39 times 19 to the power 3 divided by 12. If you calculate this value, you'll find it's equal to 22,291.75. And the units I use here, millimeter to the power 3, we end up with millimeter to the power 4. The second case I used, I'm still dealing with Ix because I'm dealing with an X in both cases. So now I'm flipping B and H. So changing B will be 90 millimeters. Now dealing with the longer dimension in the H, which is actually to the power 3 divided by 12. That flipping causes big jump in the Ix, which will turn out to be 93,921.75 millimeters to the power 4. So checking the values, that's correct. So doing now, this is Ix1, this is Ix2 for case 1 and 2. Now what's the ratio between Ix2 and Ix1? Calculate that. 93,000 around over 22,000. That's 4.21 factor. So the same cross section, by changing the orientation from here to here, you made it stiffer and stronger against bending and deflection of the bending 4 times 0.2. So that's a quick exercise on an intro into the moment of inertia, why it's so important to learn about the moment of inertia. It's translating directly into the stiffness of the beam and resisting transverse load and the bending moment resulting from it. Next for us would be, for you maybe, is to check the reading section and see what are the different moment of inertia for the different other cross sections. Check the table there, and also next would be, we'll learn in the class about parallel axis theorem, which is the theorem that helps us define moment of inertia for cross sections like this, like the T section. So it's made up of rectangles, but I cannot use this formula because this formula is for cross section, only rectangular cross section. Here I need first to find where is the centroid X, and then around this X I need to find the moment of inertia for the whole cross section. I recognize it's made up of 2 rectangles, but parallel axis theorem will help me to find now for this whole section of 2 rectangles, each one has its own BH cubed over 12, how to find the I for the whole cross section. So hold on that, we'll learn more about how to use parallel axis theorem. I hope I have good spelling here. So that we'll cover in the lecture. Very interesting topic. Hope you enjoyed and learned from this intro. Take good care and have a good night.